Log on, tune in, find out. Another good idea from Cambridge.
Are going to be a tag team, Barry Nelson and Bruce Ankerman, and they're going to talk, as you can see, about stochastic Kriging metamodels.
Thank you, Susan. Thank you very much. So there are 4 people listed on this talk, and as is typical, the heavy lifting was done by the PhD student, Shi Chen, so we didn't let her come at all. And Jeremy Stamm is listed in the program, so we're not letting him on the stage, and Bruce and I are actually going to give the talk. Now, stochastic Kriging is the term that we use for applying Gaussian process modeling to a situation where we have stochastic outputs where the variance differs substantially across the response surface. So fortunately, we're in an environment where we can make replications, which means that is estimable, but it's absolutely critical in our environment that we account for those differences. And so an additional factor comes into our experimental design, which is how much simulation effort do we put on each design point that we actually simulate. Equal effort will typically not be a very good idea, and it turns out it's also just trying to make the variances all equal is not a very good idea as well. We're not going to really talk about any of that today, but happy to talk about those issues during the break. Instead, we're going to talk about an additional enhancement, which is what happens if we have gradient estimators available along with the response surface estimators from the simulation, again with noise. So there's this very nice paper, Morris, Mitchell, and Ylvisaker in 1993 that provided a framework for saying if in your deterministic computer experiment, if in addition to response estimates, you can also get gradient estimates of perhaps various orders, how can you incorporate that into your Gaussian process metamodel to get better predictions? And they showed quite conclusively that you can get better fits overall to the unknown surface, particularly near the boundaries. And in addition, if there are, and this is sort of our addition, but if there are sort of known properties of the surface, like it ought to be non-decreasing in certain areas and so on, that having the gradient information tends to help to enforce those properties. So it is typically a good thing. Now, as you've already seen this morning in the transition that we made and in the first talks, our computer experiments are stochastic. And so the outputs that we get do have noise, and as I said, the noise differs substantially. In the work that has followed this paper, oftentimes the question is it worth the extra effort that I have to go to in the computer experiment to get the gradient information, because that's usually not anywhere close to free. Surprisingly, in our environment, in lots of problems, and you'll see an example later in the talk, we can actually get unbiased or at least consistent gradient estimates essentially for free. So with some upfront thinking, during the same run that allows us to estimate the response surface, we can also estimate the gradient. Again, we're going to have noise, and we're potentially going to have correlation. In fact, we will have correlation between the response estimate and the gradient estimate, and to a large extent, that's what the talk is about today. All right, how do we account for those things, and does it matter? And in fact, there are sometimes choices for what gradient estimator we can use, and some might have better properties for being incorporated in this sort of response modeling than others. Very quickly, given the first 2 talks, I don't really need to say too much, but I thought I'd just give a couple of examples of the sorts of things we would be modeling here. So for example, Bruce and I have had a lot of experience in semiconductor manufacturing, where the thing you're trying to predict is mean cycle time, the expected time, the mean value of the time from when you release a wafer on the fab to the fab until it completes at the end, as a function of, so our decision or controllable variables would be throughput, the release rate at which we put product on the floor, or product mix, the mix of different semiconductors that we're trying to make. I work with Jeremy quite a bit on financial engineering applications, and there we might be wanting to be able to predict risk measures like value at risk or conditional value at risk of a large portfolio of complex derivative securities as a function of the holdings I have. And so the holdings I have are the controllable design variables, and I'd like to be able to predict something like the percentile of my risk. And a classic example in operations research and IEOR is design of call centers or contact centers, where you'd want to be able to predict some sort of response time from when you make a phone call to ask what is it that's wrong with my laptop computer until you actually get to talk to somebody, right? Response time, mean response time, for example, as a function of staffing levels and the load assignments in the call center. All right, so those are responses we're interested in and the sorts of things that we might control when we want to build this meta model or Gaussian process model. And again, our systems are stochastic and dynamic, although we're not going to talk much about the dynamics today. So here, and so now for the mathematics behind this, I'm going to do everything as if x, the design variable, is a scalar. Nothing in what we do is restricted to that in any way, but it certainly makes the slides easier to put together. So the response surface that I'm trying to be able to predict by running my stochastic simulation we'll call mu of x, right? And that's the mean value or the expected value of some stochastic output from my simulation. X here is just my scalar design variable. And y with the superscript 0 is going to be an observation from my experiment, a random variable, which is an unbiased estimator of mu of x. So I can run an experiment at setting x, get a random observation whose mean value is mu of x. And y with the superscript 1 is going to be an unbiased, we're not going to deal with the consistency issues here when we don't have unbiased. It's an unbiased estimator of the derivative of that response surface, okay, mu prime of x. If you can't see how I could possibly get the second thing, that's coming in a couple of slides, right? And I'll show you where that might come from. And the model that we are going to use to represent these two outputs is that the response model looks like a mean term we'll call beta 0, a mean 0 Gaussian process we'll call mu of x, and epsilon, which represents the simulation noise. The fact that when I run the computer simulation at design setting x, I don't see the surface, I see the surface with random noise on top of it. The subscript j is for replication j, because I will always make multiple replications at any design setting that I run, and so, and in fact, control of that, how many I do, is a big issue in the sort of modeling we do. So then my observation of the derivative, my gradient estimator, we'll call that with a superscript 1, so that would be the jth replication of my estimator of that. The surface would look like mu prime, the derivative of the Gaussian process, plus another error term. Superscript 1s are associated with the derivative estimator process, superscript 0 with the response itself, the surface that I am interested in. Now, if you had a regression term as well, not just a beta 0, that's fine. Again, I'm just making things simple in terms of the presentation. So we think about running an experiment at k design points where we make n sub I replications at the ith design point, generally not equal because of the unequal variances that we would have. As I said, m is a Gaussian process, and the covariance function we'll call k. Now, I want to say a little bit about gradient estimation in stochastic simulation. This is a huge research area, and I'm only going to summarize it in 2 slides. And so I'm going to try to give you a sense of what people do in this area so I can at least link it with this model that you saw here. So remember, y superscript 0, that's an observation of the response, and with the superscript 1, that's an observation of an estimator of the derivative or gradient. So think of mu of x, the response surface that I'm interested in, as being the expected value of a function g, and g can be a function of x and a random variable z. G, think of that as the logic of the simulation, right? That's the function that turns failure times in the semiconductor manufacturing and processing times, which are random, into the actual amount of time it takes me to get that product through. And x is some structural variable about the system. So one place that x can appear is as a structural variable, right? As the number of machines of a particular type I have in the shop floor, for example. Although that wouldn't make so much sense being discrete for a derivative. Z represents the randomness in the simulation that I characterize by a known distribution f. This might be arrival processes to my call center, right? So a Poisson process that somehow describes the arrivals to my call center. And x might be a parameter of that distribution as well, right? So the x, the design or controllable variable, can appear in what we would call the inputs, which are the random processes that drive the simulation, or it can appear as a structural variable in the logic of the system itself, or it can appear in both places. And where it appears actually has a big effect on how we go about estimating the gradient. So in my notation before, an observation of my response is just an observation of g of x of z, where z represents all the randomness in my simulation. So clearly that is a random response. If I make lots of them an average, then I can get an estimate of the mean response. Now, the other piece I'm interested in is estimating, in this case, the derivative with respect to x. And so, just following along, I can think of that as the derivative of that expected value. And if the mathematical conditions apply that allow me to exchange integration and differentiation, then I can pass that derivative inside, perform a little algebra and calculus in there, and I end up with another expectation, right? So by manipulating it a little bit, I've still got the distribution f of all the randomness on the outside. And so the derivative is the expected value of this random variable. And so there is my derivative estimator. Now, a couple of things to say. I'm going to say a little more about that on the next slide. First of all, the sort of standard analysis conditions that we know that allow us to exchange integration and differentiation are really hard to figure out when you're talking about a dynamic system, a dynamic simulation of a call center, right? Because you don't have any closed form function. So a big emphasis of people who work in this area is, can I provide conditions that actually allow me to do that, right? Not the topic of my talk today, but not necessarily an easy problem. So in full generality, my gradient estimator is the derivative of g with respect to x, again evaluated at the random value z, and g of xz times this sort of score function here at the end. Now, how could we possibly go about getting those things from the kind of messy simulations that we run? So I've repeated that output there, color-coded to make it easy for me to talk about. There are two big lines of research in the simulation community about gradient estimation, and they have to do with where I put x. So infinitesimal perturbation analysis says if you can push all of the dependence on the output of x into the function g, so that the randomness z is not influenced by x at all, then the red term disappears. Right? And so your gradient estimator only involves the blue term at the beginning. So typically that's done by saying z is all the uniform 0 or 1 random variates that drive the simulation. So that's now independent of x, and all of x is embedded in g, the function that maps the randomness into the outputs. Then what we want to do is look at our simulation and say, is there a way that as the simulation runs to estimate the response that I can somehow tell what an infinitesimal change in x would have on the output response. Usually that's not so direct to look at, but oftentimes we can use a chain rule to sort of break that up into two pieces. So the change in my call center response as a function of arrival rate, that's hard to get. But the change in my call center response of the function of the actual arrival time, that I can figure out. A small perturbation in the arrival time, I can figure out what that does to the response time. And then I can multiply that by what the change in the response time or the arrival time would be as a function of the arrival rate. So very often, IPA estimators end up looking like this, and this is something you can record during the course of your simulation along with the regular outputs that you would do. Now, another major area is what's called the likelihood ratio or score function approach that says, can I push all the dependence on x into the distribution of the inputs f, and none of it is in g. In that case, the blue term disappears, and all I'm having to do is this term, and this term is particularly nice to look at because it says I'm taking my output response, g of xz, and just reweighting it by this score function approach, and that turns out to be an unbiased estimator of the gradient. So typically here we're trying to make x look like a parameter of the input distributions, the things that we specify. And when we can do that, then we have this sort of approach. And I want to quickly say, in some problems, both methods apply. In some problems, neither method applies. And in some problems, just one or the other. Okay. So now coming back to our experiment that we would run, we've got k design points. We're going to run simulations at each of those k design points. And in the simplest, and then we're going to make multiple replications at each design point. So our basic output would be the average response at the first design point and the average of multiple replications of the gradient estimator at that design point, which we've essentially gotten for free as we've gone along, no separate experiment. So we would have these vectors of results across the k design points. And our prior on that is that if we're using this Gaussian process model, is that they have a multivariate normal distribution with mean vector beta and 0 alternating, and a variance-covariance matrix that consists of two terms. One is the covariance matrix of the Gaussian process, and the other is the covariance matrix related to the stochastic aspect of the simulation, the fact that I'm only getting estimators, that I am not observing the actual response itself. So in typical Kriging type modeling, this term doesn't appear, or it appears with a very simple term, sigma squared I sort of term. Here it's extremely important because we don't have any expectation that we have equal variances across those. And I make a little note, two little notes here. One is, even if we think epsilon on the response is normally distributed, there's no reason to think that the epsilon, in fact we can prove that it's not, the epsilon on the gradient estimator is normally distributed. And so averaging is actually really important here if we're going to be using any sort of Gaussian assumptions on what's going on. The second thing, which is our real savior, is that this sigma epsilon is estimable. Because of the fact that I have replications at each of the design points, I can separately estimate that term and distinguish it from the Gaussian process. Okay, so to make this all crystal clear, we hope, let's just suppose that there are two design points on this scalar function. So x1 and x2, and I'm going to run simulations at those points. And what I'm saying is that I want to observe the response at those 2 points, and I can observe the derivative at those 2 points. Except that isn't what I observe. What I do is I make multiple replications at x1, and I average them, and that's my response estimate. So it will not sit right on, typically, unless I'm very lucky, right on the actual response. Right? It's an estimate. I know something about its variance because I can estimate its variance, but it's not going to be there. And the same is true of the gradient estimator, or the derivative estimator, because it is an estimate as well. Similarly, at the second point, I'll make multiple replications there. I'll average the results, and that'll be my estimate of the response, which almost certainly doesn't sit on the curve, and the same thing with the gradient estimator. And we're trying to take this type of information in order to be able to make predictions about what this mean value curve is. Right? That's the setting in which we're in. Now, I'm going to keep the 2-point problem for just a minute to talk about the main issues that we studied. So we've got 2 points, a derivative and a response estimate at each point. So remember that our assumption, there are 2 terms in the structure. There's the term related to the Gaussian process, sigma m, and there's the term related to the dependence among our estimators, the y sup 0 and y sup 1. And just again, to make the notation easy, I'm going to suppose I make equal replications at each design point. In general, that wouldn't be what I would be doing, but that might be where I would start in a first stage. Okay, so it's well known that the covariance structure, and this is one of the really nice things of the Gaussian process, that the covariance structure, including the gradient estimates, depends on the original covariance structure. So no new parameters that need to be estimated are introduced. And in fact, because of the nature of the structure I need to have on the covariance, I know that these terms are 0 to start with. So I have a little bit of structure right there. Now, when I come down here, I'm looking at the variance-covariance matrix of the response estimate and the gradient estimate. And this is design point 1, and this is design point 2. And now, if I choose to run those simulations at the 2 design points independently, different random numbers, then I know that this happens. Right? There's no dependence between what happens at the design points. In earlier work that Shi Chen has done, we've shown very conclusively that when our goal is prediction, common random numbers is a bad idea in these stochastic Kriging models. We actually do want to simulate the design points independently. Right? So we get a little structure there. So the real focus of the talk, now several minutes into it, are these terms. The blue term which are the variance of the gradient estimators, of the derivative estimators, and the red term, which are the covariance between the derivative estimator and the response. Now, what we did was to look for some tractable models where we could actually see what the impact of those terms would be. So we looked at two models. One is a model with two response estimates but only one gradient estimate. That allowed us to completely grunge through the math and see what the effect of every term was. And one additional one, which is a k design point problem in p dimensions, but two things. One is you only have gradient estimate on one dimension, and the design points are widely spread so that there's not very much dependence, spatial dependence between those design points. And that's a stolen idea from the paper that I cited in the beginning. And so at a high level, these are what we were able to prove with those two cases. One, it's always good to include the gradient estimators if mean squared error prediction is your goal, right? So that's a good thing to know. Not surprisingly, the heavy hitter is the variance of your gradient estimate. That has a lot of effect on how much reduction in MSE that you get. That makes us prefer infinitesimal perturbation analysis to likelihood ratio score function because invariably the variance of those estimators are much smaller. When IPA applies, it gives us much smaller gradient estimates. Now, when we look at the effect of the correlation between the response and the gradient estimator, that turns out to be complex. It turns out to matter very much where the point you're trying to predict is versus where the design points are in terms of saying what's a desirable correlation structure. And our overall conclusion is you're just better off if there's not very much correlation in absolute value between the response estimate and the gradient estimate. And that would say that you would actually prefer the likelihood ratio score function approach, which tends to have less correlation. But variance is by far the heavy hitter, and so we would tend to prefer IPA when it applies. Jack, were you going to? Okay, all right. So at this point, I'm going to turn the talk over to Bruce. We're going to be the only tag team match we've seen so far. And he's going to talk a little bit about one set of experiments so you can get some idea of what this does.
Okay, so we, in addition to these analytic problems that we were able to work through the entire math, we also tried a number of fairly small toy problems that actually have we know what the actual true surface is. So these are analytic up to the point where we know what the true mean surfaces are so that we can check to see how well we're doing. On the other hand, they are more realistic in that they have a true setting. So we did a couple of different ones. We did some queuing models. We did some project scheduling models. But the one we've chosen to present here is an inventory model. You can think of this as a fuel supplier or petrol supplier if you are here from the UK. You have a large tank, and petrol stations will send their trucks to get orders from your tank, and what you're trying to do is you're trying to minimize your cost. At the end of each week, you can order more petrol. So you have this large tank that's going to be over the week. People will come and take petrol out in the trucks, and that will be a random process. And your job is to try to minimize your long-term costs. You will be there are two levels. The first is S units. That's the small s unit is the number of units that you have set. If at the end of the week I'm below that value, I will order more petrol for my supply tank. If I will always order up to large S units. So small s and large s are sort of the control parameters that you're trying to set using this simulation. What is the level at which I should order, and what is the level I should order up to? We're actually going to use two different parameters. X1 will be small s, but X2 will be the difference between large s and small s. The reason we use the s and the small s is because that's the traditional way that it has been presented in the literature. Demand is stochastic. That's the people ordering. There will be both ordering costs, purchasing costs. There's cost to holding the fuel, so you don't want to have too much fuel held for too long. And there's also shortage costs. If you run out, people will still order, and so in some sense you can have negative supply, right? When you go into the next week, you might actually not have, you might have more than what your tank holds as what you owe. So there will be costs associated with that. You might have to give a discount to people who are having to wait. Again, the long-run total cost is your goal. And because these x1 and x2 are structural parameters, right? These are not parameters of the distribution of the error. The IPA gradient estimates make the most sense. All right, so here is the true surface. As I said, we know what the true surface is for a given s, small s and big S. And notice we've got x1 and x2, the large S minus small s on the axes. And this is the true surface. There's two things I want to talk about on the true surface here. Oh, this is the predicted cost per period. The first is, this is an actual surface, but we've got it represented as a grid, and that helps to talk about what we're going to be measuring as our output. Because what we're interested in doing here is getting a surface that predicts well across this area. And so if you think of each of these, where's the button, that one. If you think of each of these crosses as a grid point, we're going to look at the difference between our prediction and the true surface at each of those grid points, about 2,500 grid points across there, and that's how we'd be estimating our mean square error. In addition, you can also think about a Latin hypercube across here. Now we've finally gotten back to the Latin hypercube scenario. We put a Latin hypercube design across this area, which is obviously at a much lower density than the grid points for the actual fitting of our Gaussian field. Now, I guess one other thing I wanted to point out is the way I want to present this is rather than showing it in 3D, because a 3D surface is difficult to see departures from, we've taken slices. So I've sliced it at 10, oops, press the wrong button again. There, that's the one I want. We've sliced it at 10, 20, 30, and 40 to be able to look at the discrepancy between the fitted surface and the actual surface. So here are the slices for 10 and 40. These are at the two ends. So notice again, here's the reorder point here. It's sliced at 10 of the x2, which is big S minus little s. The crosses are the true surface. The red line is the stochastic Kriging without using the gradient. So if you just said, I'm going to use the standard stochastic Kriging without using any gradient lines, that would be the fitted surface. The blue line is the stochastic Kriging with the gradient, using the IPA estimate gradients. And you can see that although the red line, the stochastic Kriging, is not too bad, the blue line is better. And then over here, there's two things. It's substantially worse without the gradients. The red line shows that the fit is substantially worse. Another thing to point out is that if what you were really interested in was what is the proper value to minimize cost on this reorder point small s, you would see that in fact the minimums are not the same. So even though, so in addition to having poor prediction, it also is not telling you the correct minimum value, which is critical. The other two slices didn't really show basically that the adding the gradients helps a little bit, but not so much. So again, just a demonstration of how the gradients in general helped, and this is what we saw in the other examples as well. Last slide is on the example is the box plot of the absolute deviations across those 2,500 grid points that I pointed out, and you can see that the slices showed that there was substantial improvement, but in addition, across the entire surface, you can see that there's substantial improvement in terms of the fit of the surface. So final thoughts are in dynamic stochastic simulation, we can get these gradient estimates sort of for free. It is critical to realize that the gradient estimates that we're talking about do not involve running additional observations of the simulation. If that were true, this might not be the right way to go, because you can put those replications, those design points at other places that might have better effect. But if you have these gradient estimates that are sort of part of the simulation run, those come somewhat for free, although there's some upfront work that you have to do to get them. In those cases, we are able to show that using those gradient estimates can provide better predictions of the surface. Clearly, as Barry pointed out, the number of replications that you put at each design point is something that's important in stochastic kriging, and we're hoping to be able to use this kind of analysis to help us to do that kind of experimental design.
Just one of them. We'll let you decide.
Yeah.
Okay, next up is Jack Kleiman.